Hello and welcome back to this last part of chapter 2. We're going to start off here looking at how to measure an association between two variables. That is, we want to see if there's some relationship as one variable changes, does the other variable change in a similar way or a dissimilar way for all of the observations that we see. So one way to do that is to do a scatter chart. And so we'll look at that. We'll also looking at covariance and a correlation coefficient. So a lot of this again should be reviewed from your statistics class. So in the example in the book we might want to look at, okay, are water cells influenced by the temperature outside? That is, we might guess or hypothesize that as the temperature goes up, the amount of water cells increases as well. So that would be a positive relationship or a positive correlation if we should find it. So the scatter chart then just plots the data to see if we can visualize any kind of relationship. And so if we look at what's in the book, we can see that there is or appears to be a relationship there by just looking at the data. When we see this chart, we also can see that it looks like there is a linear relationship. And so a straight line could be used to actually approximate that relationship between the temperatures outside and the sales of bottled water. So here's that chart, and you can see we could almost draw a straight line through those points, and that would be a linear regression line. But for right now, if we plot our data out, we can see, okay, this looks like a linear relationship, and that might also indicate to us what statistical model we might want to use. And so in order to map this relationship or predict this relationship, so using linear regression would be one example. Now, if this dots were sort of like this, then we know that it was a nonlinear relationship when we look for some other statistical tool to help us model that. And if the dots are all over the place, we could probably say, okay, there doesn't appear to be a relationship. It's not worth the effort to continue on searching for some kind of statistical technique to see if there is a relationship. But we might want to look for some kind of statistical technique to prove that there isn't a relationship. And we'd want to prove that at probably the 95th percentile of confidentiality, and saying that no, there's no, 95% of the time, there's no relationship there. We're confident about that. The next thing you could do to see if there was a relationship between two variables was calculate something called covariance. And so covariance is a descriptive measure of the linear association between two variables. So notice it says linear association. So if we do a sample covariance versus a population covariance, it's the same sort of symbol changes again. We'll use a little s for sample and the Greek letter sigma for the actual population. So basically all we're doing is summing the difference between one set of observations and its mean and another set of observations and its mean, and dividing by n minus 1. So if it's the population, we do the same thing, but now we're dividing by n. Also notice that we're doing the subtraction here, that difference between one set and its mean, and then we're summing that other set and its mean, and then multiplying them. So here, using that data from our book, we can see we've got data set X, data set Y. We'll then calculate the differences and then multiply them. We sum all those up, and that's where this 166.42 is, and n minus 1. So it's 13 equals 12.8. So this is a positive number, so that's a positive relationship between these two variables, that is of high temperature and the sales of bottled water. And so you can look at the graph or you can look at this, but what it's saying is that as high temperatures increase, then the sales of bottled water increase. I think it'd be a little difficult to say that as the sales of bottled water increases, then the temperature is increasing. So you wouldn't say that. So other things to keep in mind is if your covariance is near zero, then the variables are not linearly related. That's about all you can say there. If it's less than zero, then you would say that the variables are negatively related. That is, as one increases, the other decreases. So to do this in Excel, again, I think you should follow along in your book. You're going to use, let's say B17 here. You're going to use covariance.s, and then you can also use a correlation coefficient, use coral, and specify the two values. Fairly easy to do. Just make sure you understand what ranges or arguments you're putting in each of these functions. So here are some examples of some scatter diagrams you might see. So this one appears to be a positive relationship. This one seems to be, there's no linear relationship, so it probably have something close to zero for its covariance. And here's a negative relationship. And so it would probably have a negative covariance. So the correlation coefficient measures the relationship between variables, and it's not affected by the units of measurement for x and y. So the way that's done, and you've probably seen it as r sub x sub y, we have the sample covariance, which is in the top or the numerator, divided by the multiplication of the standard deviation of x times the standard deviation of y. Just keep in mind if they're talking about the population, then the values here would change from S to sigma, and you would use those formulas that you're using for sigma for the population to get a correlation here. The correlation coefficient is going to be between -1 and +1. If it's less than 0, then it's a negative linear relationship. If it's near 0, there's no linear relationship. And if it's greater than 0, it's a positive linear relationship. Typically, if you want to see a really strong relationship, you're going to want those closer to either +1 or -1. So again, using the example from your book, if we want to calculate that correlation coefficient, we would need to know the standard deviation. We'd use 12.8 and then multiply the standard deviation of x times the standard deviation of y, and we'd get a correlation coefficient of 0.93, which is a strong relationship, which means that if you think of, let's see, let me see if I can draw a line for you. Hold on. So let's think a line like here. So what that is saying is that as you increase in x, you're increasing in y. Increase in x, increase in y. So that's a positive slope. So if we had a negative slope, which would change that back to red again, a negative slope would look like this. So a decrease in y leads to a decrease in x. Or if we started the other way, a decrease in x leads to a decrease in y. starting from here, so that's smaller. So it's probably better if I just did it this way again. So if we've got smaller x, we got smaller y. So that's a negative slope. Hopefully you can see what that means. So here's another example showing the scatter plot between two variables. So this one is for a small retail store for environmental control, heating and cooling, and the daily outside temperature. So what they're spending as the temperature increases or decreases. So here the sample correlation coefficient is around a negative 0.007, and that means that there's no linear relationship between the two variables. And so you can see that on this plot. And so as the temperature outside increases for cooling, the cost decreases. But as it gets hotter, the cost starts to increase again. The next part of the chapter that we want to talk about is data cleansing. What do you do when you have data that shouldn't be in your sample data set because it's skewing the results? And that data might be there for various reasons. It was entered incorrectly, it was gathered incorrectly, somebody heard it the wrong way, just kind of erroneous things that cause that to be in there. And so if it's going to skew your results, you want to try and either take it out, or you might have data that was missing. Somebody didn't want to answer that, or you couldn't collect the data. Do you throw out the entire observation of all the different variables that you're collecting data on? So that's what we're going to talk about in this section. So what is missing data? So missing data is where you're missing values for one or more of your variables. Sometimes that can be legitimate missing data. That is, you were asking a survey question and you had a subset of an answer or another question based on how they responded to a previous question, and because it never got there, it was left blank. And so there's no data for that. So that's legitimate missing data. Otherwise, the data then might be called illegitimately missing data. And so there's a couple of different things that you can do. So one is you can discard the observations, that is, that entire row of missing values with any missing values. So let's say you had 50 variables you were collecting per person. If one was missing, you'd throw out the entire row. Well, if you do that, then you're throwing out a lot of other information that you've collected that might be useful. So just be careful when you discard an entire row. You could discard any variable in a column with a missing value. So let's say you missed a value out of one particular column, which is the variable, then you throw out that entire variable. Again, you're throwing out a lot of information that you collected from the other data points. So you may not want to do that. Then you could fill in the missing entries with estimated values. Then depending on what kind of data it is, how are you going to estimate it, and how's that going to be consistent? Or you could actually apply a data mining algorithm that's going to handle those missing values. So your book then says, okay, we can classify those missing values as missing completely at random. This is where the observation is missing some variable randomly. You don't know what caused it, but it just seems to be missing every so often. Doesn't depend on either value of other missing data or other variables in the data. So it's just, like it says, random. Then there's missing at random. So this is where it's missing a value for some variable and is related to the value of some other variable. So it might be that somebody doesn't want to answer based on, what their salary is. So if they got so far and they got to the salary question, then they intentionally leave it out. So that may be more of a better example of missing not at random. So here you've got, you've asked salary or how much their spouse makes or household income, and that tends to then cause it not to answer other questions. So as we mentioned earlier, if you don't want to throw out the variable and you don't want to throw out the record or the row of data that you've collected, then you might want to replace those missing values with something that seems reasonable. Sometimes it might be the average of the other variables for similar responses, but then you got to think about what are the similar responses. So my example there would be, let's say you're collecting values on, say, car choices for different age groups. Well, you wouldn't just say the average of all age groups for a missing piece of data. You want an average of just that group that has their average. So if it's the group from 26 to 35, you would just get that average and plug it in for any missing values in that range. The next thing in your book is an example of how to handle missing data using this Blakely tires example. I'll let you work through that and see if you have any questions. Fairly straightforward. Just pay attention to the functions that you're using. Notice you're using standard dev.s for sample population versus the actual population. And you're using a function called count blank to count the number of observations you don't see. So I guess one caveat here of when you're working with spreadsheets, if there's nothing in the cell, then that's blank. Okay, if there's a 0 in the cell, that means somebody put in information, and that's not the same as a blank. And so when you're counting blanks, it means nothing's in there, not even a space bar. Because if you hit space bar and hit return, it appears as nothing on the screen. But to the spreadsheet, it means there's a value in there. There's something in there. So you have to be careful about not doing that when you're working with spreadsheets. So they walk you through a process of, okay, let's put in some missing values. Is it reasonable to assume that for this particular tire, we could just do an average of all the other tires and put it in there? And that seems fairly reasonable. And so that's how you might want to handle that missing data. So some other things that you want to think about, and we've mentioned them already, is those erroneous outliers and erroneous values. Does it seem reasonable that a certain value is in your data set? So you might be asking for age, and all of a sudden you come across an age that's 1028. That doesn't seem reasonable. So you need to either go back and figure out why that was put in there. Was it accidentally somebody typed in an extra number somewhere? Or should you delete it and then put in some other means of estimating a missing value for that area? So we've talked about when you're looking at your variables, do the summary statistics, look at your frequency distribution, any bar charts or histograms, z-scores, scatter plots, correlation coefficients, and other tools that you can use to uncover your data quality issues and outliers. Most software that you're going to use, like a statistical software, is going to ignore missing values and calculate the various summary statistics. So earlier I was talking about with Excel, if you put a space in there, that's counted as an N. That's part of your sample size now, even though it's blank. So if you have some of that in there, your calculations within your spreadsheet is going to be wrong, especially when you're doing your standard deviation for the sample, right? And then how are you going to do your missing values? Sometimes on more sophisticated software, it will fill in those missing values for you. Or you might have to say, well, omit those cases. And when I say cases, that would be the row in your data that has all the variables. And so a lot of times, the first place you'll start is the max and min of your variables, and then you can see if that's reasonable or not, and then you'd be able to tell if you've got some erroneous variables or not. So the last thing to mention is sometimes you run into a lot of variables that you've collected, and so you might not be able to analyze them all because your computer isn't fast enough or have enough memory in order to do that. And so then you might want to do some kind of dimension reduction. And that means you're going to remove variables from your data set without losing a lot of crucial information. So that's where the correlation coefficient comes in handy. So you might have several variables that are highly correlated, and so if that's the case, you'd only need to use one of those and you could eliminate the rest from whatever calculations or modeling you might be doing. Also, you may run into data sets where individual columns of data by themselves don't really give you much insight, but when you combine them with other columns to make up a new variable, that might reveal some important relationships. So those are the sort of things we'll be discussing throughout the chapter. That ends chapter 2.